Hello. In this video we're talking about descriptive statistics and we're focusing on two important measures of spread, the variance and the standard deviation, which are very closely related to each other. Just to remind you what it is we want to do when we're calculating descriptive statistics for our data, we want to be able to quantify first of all where the data are on the number line, and we would use statistics like the mean and the median to do that. But secondly, we want to quantify how much spread there is in the data, how dispersed they are around any central tendency. And to do this, we use statistics like the variance, the standard deviation, or the interquartile range. And in this video, we're just talking about the variance and the standard deviation. And I'm going to quickly talk you through how we can calculate these two important values. So we're going to use a toy data set here. We're going to use the weights of 6 mice in grams, which we also talked about in the video on means and medians, so you might be familiar with these data. So here are our weights of our 6 mice. They go from 19 grams to 35 grams with a middle tendency around about 28ish. If we want to quantify where the center of these data are a bit more accurately, we can calculate a mean. So we add all the numbers together, which gives us 161, and we divide that by n, the sample size, and this gives us our value for the mean. So we want to know how much dispersion there is in this data set around the mean. So what can we do to give us a value for the overall amount of spread there is around this value of the mean? Well, we can calculate how far each of our data points is from the mean by simply subtracting the mean from each data point. So we would write this down as x minus x bar. So just to remind you, x bar is the mean, x refers to each data point in our data set. So for our first data point, we have a mean of 26.8 and a value of 19. So 19 minus 26.8 is minus 7.8. For our second data point, we have a value of 32. 32 minus 26.8 is 5.2. And we can continue doing that for the entire data set. So we now have an indication of how far each of our data points is from our calculated value of the mean. So could we maybe use that as an indicator of how much spread there is in the data? Well, we could try, but there's a problem. And that problem is that if our data are symmetrically distributed around the mean, then roughly speaking, half of these values will be negative, half of these values will be positive. So if we were to just add all of these values together, we would, on average, get 0. We won't get 0 every time. In fact, if you add these together, you get a number that's quite a long way from 0. But on average, you would just get 0. So simply adding up all of the deviations from the mean isn't a good way to tell us how much spread there is in the data. What we need to do is find a measure which doesn't add up to 0. So one way we can do this is we can take the square of each of these deviations from the mean. And we would write this down as x minus x bar squared. So when you square a number, it doesn't matter if it's negative or positive, the resulting value is always positive. So minus 7.8 squared is 60.84. 5.2 squared is 27.04. And we can continue doing this for all of the values in our data set. And then we can add these squared values together, and that gives us a value of 214.84. This is a really important value in lots and lots of statistics. The sum of the squared deviations from the mean, or as it's more commonly called, just the sum of squares. And we'd write this down formally in this way, so that capital sigma on the left, it says add everything after me together, and then x minus x bar, you've seen that's the deviations from the mean, so you subtract the mean from each value in your data set, and then we put brackets around that, and we're going to take the square of that, and that's the sum of the squares, or the sum of the squared deviations from the mean. So can we use that as a useful indicator of how much spread there is in our data? Well, we can, and it's going to tell us something, but if we're just interested in how much spread there is in the data, this isn't a very useful statistic. And the reason it's not very useful is that as you add more data points to your data set, it's going to get bigger. So if we added another 6 values into our data set and those values had roughly the same amount of spread around the mean, then our sum of squares would be double what it is for the current 6 values. So the sum of the squares isn't really a useful indication as to how much spread there is in the data. It is useful in lots of other things in statistics, but we're not going to talk about that today. So what can we do? Well, we could try and standardize the sum of squares for the number of data points in our data set. So we could just say, well, what's the average value for this for each data point in the data set? So we could just divide by the sample size. And that sounds like a useful solution. But there's one problem with that. And the problem with that is that almost every time that we're calculating something like this amount of spread in the data, we're calculating it from a sample rather, not from a population, sorry. We're calculating it from a sample that's been sampled from an overall population. And if we just divide by the sample size, then our estimate of the population variance, because that's what we're calculating, will actually be a little bit too low. So what we actually divide by is not the sample size, but a quantity called the degrees of freedom, which is a rather complex concept in statistics. I'm not going to go into detail about it. All I'm going to say is that for our purposes here, the degrees of freedom are equal to n minus 1. So n is equal to 6, so our degrees of freedom are equal to 5. So we divide by the degrees of freedom, and that's effectively telling us how much dispersion there is in the data set, and it gives us a value that we can compare between lots of different data sets with different sizes. So this value that we've calculated is called the variance. It's usually represented by the lowercase Greek letter sigma squared. We've seen that we can write out the sum of squares as sigma x minus x bar squared, and then the degrees of freedom are n minus 1. So this is the full formula to calculate the sample variance here. And in our case, that's equal to the sum of squares that we calculated divided by 5. And so the variance for our data set of mice is 42.968 or 42.97 or 43.0 if you want to round it off to 2. And that's a value that we can use to compare between data sets. So if we thought that for whatever reason our mice were particularly variable in their weights, we could ask someone else who's using similar mice, how much variance is there in the weights of your mice? And they might have answers from 120 mice, but we can make a meaningful comparison between their variance and our variance. So the variance is a very useful statistic. A second very useful statistic that's closely related to the variance is something called the standard deviation. The standard deviation is usually represented by a lowercase sigma. You probably remember that the variance is represented by sigma squared, and to calculate the variance we take the squared deviations from the means. So to calculate the standard deviation, all we do is we take the square root of the variance. Or if we want to write it out fully, we calculate it this way. In the case of our 6 mice, we know the variance was 42.968, so the standard deviation is the square root of that, and so the standard deviation is 6.55. And the standard deviation is another very, very useful quantity that we can calculate that tells us important things about our data. If you're dealing with normally distributed data, then all kinds of important things follow if you know what the standard deviation is. So as one example, or if you have normally distributed data, then 95% of all the values in your data set should be within 1.96 times the standard deviation from the mean. So you can find out important things about how your data should be distributed in your data set if you know what the standard deviation is. And it's very simple to calculate it. If you already have the variance, you simply take the square root of the variance. Okay, that's enough. Thank you very much.